Bleh.
Hello, Mr. Ryan, right? What are those?
Binary trees.
Binary trees. Okay, so we talked about many binary trees problem before. Okay, so today we're going to find out how many paths, how many paths from the root to the leaves. Leaves are the nodes which do not have any kids. Okay, the root is the only node in a binary tree in a tree which doesn't have any parents.
3.
So we want to count how many paths from the root to the leaf node. Okay,
3.
and
3.
wait.
3.
I haven't finished yet. Okay, so let me continue. So all these nodes are
3.
between 1 to 9. Okay, so the node value is between 1 to 9. Okay, inclusive. So we want to find out that the path from the root to the leaves, which by collecting the nodes and find it out if those nodes we collected can form a palindrome.
3.
Palindrome. What's palindrome?
Wait, what?
Palindrome.
No.
When the reverse is the same.
Okay, so for example, in this case,
No.
come on. In this case, if this is one of the roots, right? One of the paths, 2, 3, 3. We can form a palindrome by rearranging the order, so which is 3, 2, 3. Okay? And this one, no, right? 1, 2, 3, obviously no. And this one, yes, because it's 2, 1, 1, and then we can do 1, 2, 1. So there are two paths. Okay? So given this example, 2, 1, 1, yeah? 2, 1, 1, we can make it 1, 2, 1. What else?
2, 1, 3, 1. No.
No.
2, 1.
2, no. Probably no. Yeah, that's the only one, right?
That's why we should get a dog.
How is that
Let's
related?
try.
Nice try. Okay. So we want to count how many paths from the root to the leaves in a binary tree, such that the path.
What if there's only one node?
One node is is one single node a palindrome.
Yeah.
Yeah, then yes.
Yeah.
Yeah, for example, like 4, then yes. Okay. Okay. So if we have another example, 2, 3, 4, 2, 1, 4. Okay, so how many paths?
Why are the 4 not connected?
1.
1, which is
Maybe.
2, 4, 2. Okay,
Yay.
and then that's it, right? 2, 4, 2. Okay.
Yay.
All the nodes.
Wiki!
Okay. All the nodes are given in a range from 1 to 9, a single digit or a single digit. Okay. Any thoughts about this? How do we check?
We
Just
just
take
brute force.
brute force. Yes. Okay. Brute
And
force.
then check if we can make a palindrome.
How do we check? For example, like given a list of nodes, how do we know? How do we check if we can form the palindrome?
If two nodes are the same.
Sorry.
If the length is 3, then if 2 nodes are the same, then you do it.
No. For example, I forget about the binary
That's
tree.
what I said.
Forget about binary tree. So I'm
And
giving
if
you.
there's 4, then if two nodes are the same. 2 nodes are
Okay, so can we?
Pairs of nodes are the same.
Okay, so can we make a palindrome out of these?
No.
1, 3, 3,
Yeah,
1.
Yeah.
Yeah.
1, 2,
Okay.
1, 3.
1, 3, 3,
2,
1.
3, 1, 3, 2, 3, 1.
Can we make a palindrome out of this?
3, 3, 3, 3, 3.
Can we make?
No!
No. Okay.
Because they're 4 and 2 and 1 in the same blur.
1, 3, 1, 3, no, 3, 1, 3. 3, 1, 3.
Can we make a
Where's the
palindrome out
2
of this?
going?
3, 1,
Yeah,
3.
4, 2, 2, 4, 2,
Yeah.
4, 4.
Okay, so what are those in common when we can make a palindrome? What are those in
Two
common?
nodes are the same, that's what I said.
2 nodes are the same, but
Yeah.
not 2 nodes are the same.
If the length is an odd number, if 2 nodes are the same, if it's an if you do it
If it's 3.
no wait if the length is an odd number, then you just divide it by 2, which should give you
You subtract 1 and then you divide by 2.
no, you can divide by 2 and then ignore the rest. Or
No.
ignore the-
Okay, so how many types of palindrome?
And then if the amount of number of the pairs is the same as if it's divided and removing the decimal. And
So how many types of palindromes are there?
1 palindrome, 2 palindrome.
No, in terms of the length. How many types of palindrome? In terms of
Two.
length? 2. Which are
4.
the
Odd
odd,
and even.
odd and even. Okay.
Ho ho.
For the For the even, we could have something like A, B, C, D, and then
Abba.
E, B, C, B, A, right? Something like that. So
Abba.
these in
Abba.
pairs, right? These in pairs. So meaning that each character has even number of occurrence, alright? Like, yeah.
What?
If it's even palindrome, it means that each character has even number of frequency. Right? Right? Makes sense? Because each one comes in pairs, so it's even number. But for the odd number, so it's like A, B, C, D, E.
Only one.
And then-
only one of them.
And this in middle, it could be anything,
Only
right?
one of them is on its own.
Yeah, so yes, so only
Yay!
one is the odd, right? So we can rephrase this. If the number of frequency, the odd, we count those elements which have the odd frequency. If there's only one or less, then we can make a palindrome. Otherwise, no, right? For example, these we count because look, 2 and 1, they both appear one time. There are 2, so which is not. This one is okay because we can make a palindrome out of these because there's only one element which is appear once, which is 2, right? So we want to count the number of the frequency that appears only a odd number of times, and there can be only one. Okay?
Yeah, but what if A, B, C, wait. No, wait, sorry, okay, let's do this one. 1, 3, 3, 2, 1.
Yeah?
Uh,
Yeah? Now we can make a palindrome out of this.
Yeah. If there's 2.
Okay? So what are we doing with this? We cannot because look, 3 appears.
We can because.
Oh, yeah, we can, yes.
1, 2, 3, 3,
Yeah.
2, 1.
Yeah, we can, yes. Because 3 only appears, only one element which appears odd number of times, which is 3.
Yeah,
Okay.
yeah.
But if it's another one, we cannot, right? This is simple, right? Because for this one, there's no odd number of frequency. But for this one, we can only accept one which is in the middle. We can put that extra one in the middle, right, to make it a palindrome. So we know how to make a palindrome here. So by brute force, how can we brute force the binary tree? How many options do we have? What are the orders to traverse the binary tree?
Breakfast search, deficit search.
Breakfast search, depth search. Yes, breakfast search, depth search. Level by level, right? This is breakfast search. Depth search, we just travel, as deep as we can. If not, we go back. So this question is quite simple now, right? Because we can use the brute force. We can travel the binary tree using whichever order, right? Depth search, breakfast search. So today we talk about depth search. Depth search, we can implement it using 2 ways. One is the recursion, the other one is the iterate using the stack. The same idea, just different implementation details. So we just traverse the tree using the depth search. Then we need to count, right? We can use the hash set, we can use the array to store the number of digits and their frequency when we traverse along the path, right? And then once we reach the leaf node, we count how many. We need to count how many elements have the odd number of frequency. If it's less or equal than 1, then we can make a palindrome. We can make a palindrome out of it. Okay? So there are 3 ways the 3 ways when we traversing the nodes to the leaf node. We can use the array because I said at the beginning there are only 9 possible values for each node. We can define an array which is size of 9 to remember the frequency, to count the frequency. For example, okay, 2, we meet the 2, so we just have this array 2 plus equal 1, right? 3, then array 3 plus equal 1. So we can do it, or we can use a hash set, okay? Let me quickly write one of the approach, which is using array, okay? And then I'm going to tell you the other tricks to speed up the implementation. Define depth search, the root, okay? If not root, then we can return 0, right? If it's nothing, we return 0, okay? So now...
If it's nothing, is a palindrome.
Yeah, okay.
Because when you reverse nothing, it's still nothing.
Good point. Oh, good point. Okay, so because we are dealing the case in the leaf node, right? So we're dealing the case in the leaf node. So we will return 0 for now. Okay. So now the second parameter we need to pass in state, which is the number of digits and their frequency. So we have this like sin. Okay, sin. This is an array which is size of 9 from 0 to 8. Okay, so now we have seen this root, right, once. So sin root of value minus 1 because it's from 1 to 9, right? We want to map it to the array index which is 0 to 8 plus equal 1. Okay, we have seen this once, right? We have seen this once. Now we have seen this one, so we want to answer at the beginning equals 0. Answer plus equal depth first search root of left. We visit the left tree and we pass in this. So we have to pass over a new state, which is this one. Okay, and then answer. Similarly, we need to depth first search, perform the recursive depth first search on the right subtree, and then with the new state, which is sin. We use this syntax, right? Syntax to say we perform a deep copy, okay? Because we have seen this value once. And then if root of left equals none and root of right equals none, so it means that we have a leaf node, then we have to check, right? If the sum of sin. So look, we are counting how many times this value appears. But actually we don't need to count how many times they appear, right? We just need to know whether this is odd number or even number. Am I right? We don't need to actually know how many times they appear. We just need to know each value they appear odd number of times or even number of times. Am I right? Yes? So instead of plus equal 1, we can do this exclusive or equal 1. What does it mean? Look, exclusive. Remember this or thing, right? Or thing, or n, right? Do you still remember? Or one of them is 1, Otherwise it will be false. And needs both cases to be 1. Am I right? This is exclusive or. What does it mean? Okay. So let me write this. This is A, this is B. Okay, so let me write this way. If this is or, right? 1, 1, 1, 0, 1, 0. Okay. 1 or 1 is 1. 1 or 0 is 1. 0 or 1 is 1. 0 or 0 is 0. Right? Do you get this? Right? Or, right? Two things. One of them is true, then it's true. Okay?
Wait.
And if it's n.
So 1 is true.
Okay?
So 1 is true.
Yes, 1 is true, it's true.
If it's XOR, is it basically the opposite XOR?
No. Okay, let me put it separately so we don't confuse, okay? Let me put it separately. But this is or. Or means that one of them is true, is 1, and the result is 1. Otherwise, it's 0, okay? So if it's n, if it's n,
and then it needs both of them to, otherwise it's false.
this is 1, otherwise all false, right? Because n, A or and B both needs to be 1, okay? But for exclusive or, okay, so this is n, right?
So
This-
but and is basically if one of them is 0, then it's false.
Yeah, XOR if one of them is on, then it's true. Otherwise, if 2 of them is on, then it's false.
Let me write it and then can you explain it, okay? This is 0, this is 1, this is 1, this is 0.
Okay, so if 2 of them are the same, then it's 0.
That's right. If they're different, then it's 1. Okay, this is called exclusive OR. Okay,
XOR.
exclusive OR. So
XOR.
what does it mean? The exclusive OR 1. It means that if the original value is 1.
Isn't that execute?
No, exclusive OR. So exclusive OR. So what's the exclusive OR? What's this exclusive OR equals 1? So if
That's
the original value is 1,
That's
so
execute. Right?
exclusive OR 1 equals 0, right? Because they're the same, 0.
Isn't that
And then exclusive 1 that becomes
1.
1, and then exclusive
Only
or 1, 0. Okay, so you see it targets the value. If you exclusive or 1, then you tablet, 0 become 1, 1 will become 0, 0 will become 1, 1 will become 0. So it's the same thing as if A is the value 1 or 0, then you can say A becomes 1 minus A. It's the same thing, right? It's the same thing, okay? In this case, it's the same thing, okay? As I said, we don't need to know how many times they appear. We just need to know they appear even number of times or odd number of times, right? So if we change this, then we sum it, then if it's less than equal 1, if it's less than or equal than 1, it means that we can make a palindrome out of it. Am I right? Do you get this point? Yeah? Because we are looking for only the maximum number of 1, meaning that the number of the elements which have the odd number of frequency is 1. Okay? If this is the case, then we can make a palindrome, answer plus equal 1, and we can answer. Okay? Depth first search. Look, depth first search. Let me rephrase this, okay? So depth first search, recursive function, we're passing a root node. The second parameter is the state, is the array, which is of size 9, which is size 9, okay? Representing each element representing the number of the times they appear. Actually, if they appear, the even number of times or odd number of times, right? Right? Okay? And then we perform this depth first search on the left tree, on the right tree, and then if it's a leaf node, then we check if we can make a palindrome out of it by counting. This is one approach. We can also use the hash set. This is similar, okay? But still not very convenient because we are passing this state. This is 9 elements. Every time we need to make a copy, deep copy of these 9 elements, and we need to sum all the elements in this array. Okay, because it's binary, each state is binary, right? We can use the binary. Instead of using the 9 integers, like 0, 1, 0, 1, 0, 1, 1, something, instead of dealing with those array, with 9 elements, we can use an integer to do it. Right? Each integer can be represented as the binary, right? As a binary. So instead of this, I'm going to change this. So, right? So define depth first search, sim, and mask. We call it mask. Okay? Mask by default is 0. So this is the same. If not root, return 0. And then here, right here, we need to mask exclusive or equals 1 shifter. This is root, right? Root of value. Okay, root of value. -1, it doesn't matter, okay? Because we are representing the states using the binary. And then here, this is the same. Answer equals 0. Answer plus equal depth first search, root of left. And then instead of the array, we pass the mask. Answer plus equals depth first search, root of right, mask. And then this bit is the same, right? If we have seen if we reach the terminal node, which is the leaf node, if root of left equals root of right, if root of left is none and root of right is none, if it's a leaf node, then okay. So if it's a leaf node, so now how can we rewrite this, right? Remember, we are looking for only one bit set in binary. Right? So in binary, how for example, like 15 in binary, you know, it's 1, 1, 1, 1, right? There are 4 set ones. There are 4 ones. But we are only looking for single one, or it's 0, right? So we talk about how to check if a number is the power of 2. How do we check if a number is the power of 2? We talk about like 200. That's one way. But using the binary, remember, 1 is 2 to the power of 0, right? 1 in binary is, let's take a bit, yeah? We talk about the binary, yeah? It's 0, 0, 0, 0, 0, 0, 0, 1. This is 1. This is 1. 2 in binary. What's 2 in binary?
1, 0.
0, 0, 0, 0, 0, 0, 1, 0. That's 2 in binary, right? This is 2 to the power of 0. This is 2 to the power of 1. What's 4 in binary?
1, 0, 0.
0, 0, 0, 0, 0, 1, 0, 0.
Because binary is basically using the power.
Yeah? Okay. So look. This is power of 2, right? So how do we check? What's the pattern of those numbers in their encounter? There's only single one, right? There's only single one, right?
At the end.
That's only single one. So 2 to the power of 4, 2 to the power of 3, which is 0, 0, 0, 0, 1, 0, 0, 0. So those numbers are power of 2. How can we check if it's a power of 2. Easy. If this number is n, we just have to say n, obviously n needs to be bigger than 0, right? And if we do the n and n minus 1 needs to be 0. Okay? What does it mean? Look, if we subtract 1 for any power of 2, what happened? If we subtract 1 from this, so it's 0 followed by 1, right? If we subtract 1 from this, it will become 0, 0, 0, 0, 0, 1, 1, 1, right? Okay? Remember this. If we perform an n here, what happened? Remember this n thing. We only got a 1 if both are 1s, right? So all these will be 0, right? Yeah, because look at 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, okay? So it has to be 0. So this is the expression. This is how we check if any given positive integer is power of 2, okay? So instead of this, we can just say if this mask, okay? Mask and mask minus 1. If equals 0, then answer plus equal 1 and return answer. We are only checking mask and mask minus 1. If it's mask equals 0, that's great because if all 0, it means that if all the occurrence, if we don't have any element that appears odd number of times, what happens? Then you'll become all 0, right? So it means that this is the even number palindrome. Am I right? Because all the elements appear even number of times.
But then that will be palindrome.
Yeah, it's a palindrome, yes. Okay. So this is the same idea, but instead of using an array or hash set, we use an integer. We just use integer. Why can we do it? Because that each integer we can represent using binary, and each bit there's only 2. Last few lessons we talk about binary. Why binary? Each bit has 2 states, 0 or 1, right? So each integer, right? Each integer we use this one shift root of value, right? This root of value is from 1 to 9, and then we shift the position over 1. So each bit corresponds to each digit. So for example, this is root of value minus 1. So this is representing the state of 1. This representing the state of 2, 3, 4, 5, etc. Right? So every time we do the exclusive OR, right? 1 becomes 0, 0 becomes 1, 1 becomes 0. Am I right? So at the beginning, all zeros, it means that they never appear before. It's an even number of occurrence. We have seen 1. Then we target this value, target this flag, it becomes 1, right? It becomes 1, it means that we have seen it odd number of times. And later we find another 1 here. So what happened? We target it, it becomes 0. It appears 2 times, right? It appears 2 times, it means that we need to change the state to 0. 0 means that it appears even number of times, right? And then we perform this depth search from the left tree and the right tree recursively. Next lesson we'll implement it using the stack, not using the recursion. Here we are using the recursion, calling except, right? Until we have reached the leaf node here. If root of value left equals root of right, then we simply return the answer. So this answer thing can be merged. Actually, we don't need to put that here. We just we can say answer equals that. Answer equals that. Okay. So we can save one statement. And of course, this we can move it outside. So answer equals 0. And instead, we can say non-local answer or self.answer. Self.answer to reference the variable. Okay, to reference the variable. The time complexity is O(n) because we're traversing all the nodes. Okay. The space complexity is O(n) because the recursion we have this calling stack. We have this calling stack. Okay.
Whoopsie-doodle.
Okay. Let's see. What have you learned today?
Nothing.
What have you learned today?
This.
So what's the problem?
We have a binary tree and we want to find out which way to go to the leaves and that the curve makes a palindrome.
Okay, so one question. How can we check, given you a few elements of the array, how do we check if we can make a palindrome out of it? What's the key thing to check here?
How much times it appears and one appears if it's even, and if it's an odd number of nodes, then there could be a one. There has to be one odd number.
Maximum one element can appear odd number of times, right? We can make a palindrome out of all the elements if they appear even number of times. or at most one element that appears a number of times. Okay, and then we traverse the binary tree. We can use the depth search. We can use the buffer search, as long as we pass the states from the root to the covered node. What I meant is the state is that the number of the elements and their frequency when we traverse from the root to the leaf node. Okay, that's it for today. Bye bye.
Bye.
Bye bye. Bye bye.